This is a production of Cornell University.
All right, so this is a picture I took from my iPhone in 2012 when I actually was a postdoc at NCAR, the National Center for Atmospheric Research, when we were evacuated from this building that hopefully you can see on the right there. This is the Mesa Lab in Boulder, Colorado. These fires of 2012 were quite severe. And the lightning bolt that set this one ablaze happened at about 1:10 in the afternoon. We all heard it, thought, well, that can't be good. That sounded really close. And then within about 15 minutes, by 1:30 in the afternoon, there's a little trickle of smoke, just like ink painted onto the skyline. By about 1:45, it was much more of a torrent of smoke. And by 2:20, 2:30, when we were evacuated, it looked like this. The skies were darkening, and it was more akin to Mordor or something. And the advisor I had at the time, whose name was Clara Desser, she's a very famous climate scientist, she wanted to know if this was a megadrought we were seeing in Colorado during the summer of 2012 was a megadrought. That same summer, a lot of you will remember the Midwest was hit very hard by a mid-growing season drought. I was at a wedding in St. Louis and just driving around in the countryside. First of all, St. Louis in the summertime, people maybe are from that area know that it's typically fairly humid. It was dry and hot instead of being humid. And they were calling it the Great Corn Apocalypse of 2012 because the drought was so devastating to the crops there. A lot of you will be familiar with the Dust Bowl. There was a documentary on PBS recently based on the book by Timothy Egan, The Worst Hard Time. Among other things, other devastating impacts of the Dust Bowl was a thing called dust pneumonia, which affected the elderly and infants. Dust accumulated in their lungs, and they would eventually get so much mucus and just debris that it would cause a form of pneumonia that was an infection, ultimately causing many people, young people and old people, to lose their lives to dust, to drought. In an interview about the Dust Bowl and about his book, The Worst Hard Times, this is what Timothy Egan wrote. I think this is a really captivating quote. I'll let you read it yourself since you can read faster than I talk. But he makes the analogy to Hurricane Katrina. And he says the grass protected the land against the ferocious winds, cycles of drought, and dust and storms. And so you have this exodus, migration of people, very famous exodus out of the Central Plains during the Dust Bowl, which had become the breadbasket before that event, an exodus to places like California, other parts of the US in the 1930s. And then the title of the book gets its name, The Worst Hard Time, because people who lived through that horrific experience, and some of them went on to endure the Great Depression and World War II, still referred to the Dust Bowl as being the worst episode because year after year the rains just failed, and in an agrarian society that was very, very painful. 1950s drought, lesser known but very similar in magnitude, affected the Southwest. I got an email after some of our studies were published from one of our Cornell alumni who he's a fourth generation farmer in Texas. And he talked about his family's, his family's memories of the 1950s being very, very bad, really, really bad. And then, of course, there's what's been happening in California more recently. And the same question comes up: is this a megadrought? Was the 1930s Dust Bowl a megadrought? Was the 1950s drought a megadrought? Is this what we're seeing now a megadrought? And the answer to all those questions is no. A megadrought is worse. A megadrought is much longer lasting. These are intervals of aridity that are defined primarily by their duration and have been linked to the demise of civilizations. This is captured very nicely in the Wikipedia entry. So, showed this at a scientific talk a few years ago because I was pretty sure I knew who had written it. It's a fairly small community of researchers who study megadrought. I was pretty sure the guy was in the room, and when I showed this, he snickered, and I was like, it is you. So it's got some good juicy pieces of information in there that we're going to come back to later in the talk. 2 decades or longer, so duration. right? As bad as anything seen during the historical period. So as severe as the 1930s Dust Bowl or the 1950s drought, or even this recent one. And they may constitute a threat to civilization. This idea that in the past, in the pre-industrial period, civilizations have grown and they've reached a capacity where they have these vast networks where they're moving water around and growing crops to feed their population. And when things like megadrought, multi-decadal drought hits, it's been linked to their demise. So those are some of the key aspects that I think about when I talk about megadrought. Another way to think about megadrought in terms of the climate system in general is like the low notes, it's the base notes, the low frequency, the long time scales of variability that change very slowly compared to human life cycles or compared to times on which we have to make decisions about how to manage water or adapt to and respond to climate change. The slowdown, the supposed slowdown, or the changes in the rate of warming that have been in the news media a lot recently are also a flavor of this low frequency, these low notes of climate variability. And I'm interested in the hydroclimate component, the megadrought story on that low frequency end. And because these timescales are long, they're long compared to human life cycles, compared to the instrumental data that we have, which, if you think about how long we've been measuring temperature, maybe 150 years in some parts of the world, 100 in others, in parts of Western North America, less than 150 maybe. So the phenomena we're interested in evolves very slowly compared to the length of records we have to study it. And that's a problem for trying to characterize megadrought risk in the future. And we get around this partially by turning to paleoclimate records. These are archives of climate variations of the past, as well as global climate models, which give us information about climate variability generated by simulating the flow of energy and mass in a three-dimensional grid. And those two perspectives, combined with the instrumental record, can tell us maybe a little bit more about megadrought, the likelihood of megadrought, and the risks associated with climate change and megadrought. So I did my PhD at the University of Arizona. I'm not trying to promote the University of Arizona here. I'm showing this slide because at the time when I was there, the world famous, the cradle, the birthplace of dendroclimatology, the study of using tree rings to characterize drought over the past few hundreds of years, the birthplace of this discipline was here in the stadium, right underneath the bleachers. The nice thing about that is if you wanted some tasty nachos on a Saturday morning when there was a game, you could easily just go into your office, get some nachos. And then they would close everything down. Or if you're already stuck in the office, it was very loud. I did not have an office. I did what I would call is like a study abroad. I was in a different building studying atmospheric climate science, geoscience. I did a study abroad across campus and worked for a semester in the world famous tree ring lab, which at the time was in the stadium. So you go in and you get your nachos, and then as soon as you go back into the other side, you cross the hallway, open up the doors into the tree ring lab, and your nostrils are immediately relieved from the smell of like putrid soda and popcorn with this rich oaky pine smell of the samples that have been collected for the last 100 years in the lab of dendroclimatology. And I learned a few things during my study abroad about how tree ring data are put together and used to reconstruct or to make inferences about climates of the past, and particularly how that relates to climate change. And I'm going to share some of those with you. This is really very basic stuff, and it's going to be familiar to most everyone. And I think it's familiar in a general sense to people who have looked at the widths of trees, in an elementary school or in a high school class setting. But there's some really quantitative, rigorous parts to it that are important to try to understand to be able to have confidence in our estimates of past megadrought climate variations. So let's just start with the ring width measurements. They go into the field, and these dendroclimatologists, it's kind of an awesome job. Their summer season is just basically walking around mountainsides with these old Swedish coring devices. These are pieces of technology that were invented in the 17th century to do forestry in Scandinavia and Sweden. So they go. It's a 400-year-old piece of technology that takes a very small core, just a small little thin round sample of wood. Ideally, if you're good, and I wasn't, but if you're good, you can get all the way down to the pith of the tree rings, and then you can get basically the whole lifespan of that tree. When I went out into the field with some of these guys, I was able to core three trees in the time that one of the guys I was with scored 24. You get really buff shoulder muscles and back muscles too, because it's really hard work, especially as you get deeper and deeper in and the pressure increases. So you go out and you take more than 3 samples. Usually 24 would be like a minimum, maybe more like 40 or 50 samples from different trees. And there's a lot of science that goes into site selection, because if you're interested in hydroclimate, if you're interested in precipitation in the past, you want to pick trees that are growing in places where moisture limits their growth. Why? Because during wet years, they're going to grow more. And during dry years, they're going to grow less. If you pick a place where moisture isn't a limiting factor, where competition or sunlight or something else is the limiting factor on growth, temperature, then you're not going to get as clean of a proxy for precipitation changes in the past. So there's some site selection that's really basic to making these records, putting these records together. These are the individual samples in units of millimeters on the y-axis that are measured during the other 9 months of the year. Once you get them back to the lab, you've got your nachos, you sit down and make some measurements of the widths of the cores that you sample. And they're going to be of different lengths because trees are different ages, or because in my case, the ones that I cored didn't actually hit the pith of the tree. So actually, you imagine like the core of a tree, you go sideways through it and you miss the center part, and you're actually starting to sample rings that you've already sampled on one side of the tree. So that was my contribution to the science. So you have to chop that out. You don't use that part. So you've got different length segments, and each one of them has some non-climate information. Some contribution to the growth arises from factors other than the amount of moisture available for growth during any given year. And that, in the most basic sense, you could think of as being the fact that as a tree grows, it's getting to have to put on more and more wood, so its radius is increasing, and so for the same amount of photosynthesis, for the same amount of productivity, it's going to have to make narrower and narrower rings. That's one way to think about it. The other part of it is that trees tend to shift resources away from growth and towards reproduction as they get older. So older trees do less growing and more, setting out seeds and thinking about the next generation. So this red curve here is a spline. It happens to be a spline. It's a function that we fit to the raw ring width measurements to try to estimate that non-climate component. That biological, that non-climate growth curve is then removed, and then you have ostensibly from each site an estimate of the climate contribution to growth, the part of growth that wasn't the tree's biological processes, but was its sensitivity or its growth that was limited by precipitation in this case. So that's for each tree. Okay, so when people talk about tree ring reconstructions and you hear about like the hockey stick and Mike Mann and the last millennium temperatures, they're not talking about individual trees. We're talking about compilations of trees that are pre-processed and then stacked together, put together using statistical methods to make a weighted average from a given site. And this is just one site. This might be one mountainside in the San Joaquin Mountains, right? This might be one stand in Mount Lemmon in Tucson. You average those together, maybe 24, 48, 50 trees, and you have what's called a chronology. Ring width measurements, ring width indices form together to make a chronology, and there is another way of essentially improving your signal-to-noise ratio. Or, in other words, if you average everything together, all the stuff that's not climate, all the stuff that's just random growth by trees, or excessive sensitivity by this one, or some insect outbreak here but not over there, all of that sort of goes away because it's all the non-climate stuff that gets averaged out. And so this black line, ostensibly, is the climate signal that's left over. And that's what we want to use to try to characterize hydroclimatic fluctuations. That's just one chronology. When you reconstruct something like Colorado River streamflow or global temperatures, you're actually using a whole bunch of chronologies. And so any signals, any information that's left in that type of a reconstruction has been massively reproduced. It's been sampled in many different ways and many different times, and so it emerges as the dominant source of variability through time. So this happens to be the network that was used in a very famous paper by Dave Miko in 2007 to reconstruct Colorado River streamflow for the last 1,000 years. And this reconstruction is shown as a percentage of 20th century averages. So in the black line here, is the cursor actually showing up there? Okay, good. Then you did see NCAR earlier in this slideshow. All right, nope, it's gone. There it is. All right, so you've got this black line, which is the observed stream flow for the Colorado River after removing the influence of dams. And then the y-axis is essentially a percentage of the average over the 20th century. And this is the classic story from tree ring science, and probably half the people in the room have heard this in one form or another. When the Colorado River Compact was being made, when the agreements of how to distribute water on the Colorado River were being made, we just happened to have been in a really wet period. And so the amount of water that people thought was going to be available long term was probably much lower on average than people estimated from the best available data in the 1920s at the time. All right. The black line, the thin black line, is the average of these. Well, it's a reconstruction. It's a 25-year running average of the reconstruction. The gray shading is just the confidence limits. And you've got these periods all along here. Woo, that's going to look terrible. So I switched from a Mac to a PC, and the next slide is going to be ugly. Fish tank, sorry. All right, and the thing that should pop out to your eye also, in addition to the fact that the period of time when the compact allocation was being negotiated, is that there are these periods where the stream flow goes way below the 20th century even minimum. All right, so those are periods of decadal or multi-decadal drought that are unprecedented in the historical record. And the work to do this was originally, some of it done in the 1970s, and it's been revisited, and it's a very robust result. In the 1970s, when the tree ring lab at the University of Arizona did this and tried to estimate flow in the past and explained it to the governor of Arizona at the time, he said it was one of his worst days in office because of the realization that the amount of water they thought would be available long term was not that high. It doesn't even factor in climate change. This is the 1970s. All right, here's the ugly slide. Sorry, I apologize. What I've done here, geez, it's just hideous. Those big, thick lines are not supposed to be big and thick, and the font's supposed to be bigger. So imagine thinner lines, bigger font. How about that? All right, what we're showing here is the same threshold. So we've got these events in the past that are 85% of the 20th century average. So that's a threshold, right? Like, those have been called megadroughts. The 1150s event. Let's go back to this one, which looks prettier. This 1150s event. This gets a lot of attention in the literature as a megadrought. There's 1 in 1,000 years. It's an 11-year period where the 25-year mean is below 85% of the 20th century average, which is a horrible mouthful to try to say. It actually works just as well if you say half a standard deviation for 35 years. It's a bad drought. It's a long-lasting, persistent drought. And so what I'm showing here is precipitation over the 20th century, and that same definition, half a standard deviation. I'm just going to find events that are half a standard deviation below the long-term average and see what I come up with for precipitation in the Great Plains, which is where the Dust Bowl happened, and the Southwest, which is where the 1950s drought happened. And you can see that definition captures those two events reasonably nicely, and it doesn't pick up on any false positives. So it's a very convenient starting point, half a standard deviation in the long-term average, running average. And so we look for that, again, in this reconstructed Colorado stream flow. We see a bunch of these things that are short-lived, but the same threshold. So every maybe every 100 years you get 1 or 2 of these decadal droughts. And then there's that mega drought, that 1150s mega drought, 1 in 1,000 years. And that ratio, 1 to 2 decadal droughts, like the 1950s Dust Bowl and the 1930s drought, that ratio of about 1 to 2 per century has held up over the ages. This is originally postulated as a ratio from a paper in 1998, one of the first papers to talk about megadrought in the scientific literature. And they also said that from their estimates, it looked like you should have multi-decadal megadroughts 1 to 2 times per 1,000 years. And since then, a lot of other data, a lot of other studies, many other syntheses, not just from the Southwest, from other parts of the world that have really rich, high-resolution, high-quality paleoclimate record, have come up with similar estimates. Not all at the same time. You don't have like global megadrought, but 1 to 2 decadal droughts like the 1930s Dust Bowl per century, 1 to 2 megadroughts, multi-decadal, 1150-style droughts per 1,000 years. What do climate models say? Now, I guess those of you who really do computational fluid dynamics know that we filter out sound waves in climate models. So climate models can't really say anything because there's no sound in the representation of fluid dynamics in a model? No CFD? Okay, it's a CFD joke. I tried. If you scream in a climate model, nobody hears you. So climate model. When I was at NCAR, a lot of what we did was run and use climate models. Climate model data, climate model output, climate model simulations. All climate models all the time. One of the chief software engineers from a group that I was working in got recruited away by Pixar. Some of you know this story. I told that story, that one of the chief software engineers got recruited away by Pixar, when I was in California, in LA, a few weeks ago talking to the alumni. And a guy came up to me afterwards and was like, yeah, I know who that was. So I was like, okay, might have to change the story a little bit to protect the innocent, quote unquote. I think they just backed up a dump truck full of money and were like, get in. I think that's how they got him. But they were interested in him because he was an expert in computational fluid dynamics. And when Shrek sails off on the ocean, they want the fluid of the ocean to look realistic. Or it turns out, as one of our alumni pointed out to me, when a horse turns into water and flows away, they want it to look realistic. Whatever that means. The way that they make it look realistic, and there's happy explosions that look realistic, and then there's like bad, scary explosions that look realistic. Anyway, the reason why our brain sort of accepts that a horse could turn into water and then flow away, or that Shrek is sailing on an ocean that looks reasonably credible, is because we are solving equations of motion on a three-dimensional grid in a way that's physically consistent with reality. And so our intuition tells us, yeah, that's an acceptable sort of portrayal of how fluid would flow with the scaling regime of gravity and density of water on planet Earth. And essentially, a global climate model is the same thing. It's a three-dimensional simulation of flow of energy and fluid throughout the whole world, both the ocean and the atmosphere, and all the fluxes between sea ice and the atmosphere and the land. It's all represented, and it's represented in a discrete number of points on this grid. And I'm not going to fix this slide. Sorry, just deal with it. It should be all black, like one sort of black box that says explosive volcanism. But the simulations I use and that I look at from NCAR and from other modeling centers around the world that run these three-dimensional simulations are trying to simulate climate not just of the last 50 or 100 years, but of the last 1,000 years. And over the last 1,000 years, it's like the backyard of climate, right? It's the backyard of climate change because a lot of really interesting things have happened. Not catastrophically, hugely interesting things like ice ages, right? 20,000 years ago, we'd be underneath 2 miles of ice. That much change hasn't happened in the last 1,000 years. It's been relatively stable, but at the same time, some really interesting volcanic eruptions have occurred. There's been some variability. You guys don't have it up there either. Not solar variable. It's solar variability. There's been some fluctuation in the output of the sun over the last 1,000 years. There's a 200-year sunspot cycle, which is related to the intensity of solar output. There's an 11-year cycle that people have probably heard about. These are small fluctuations, but they could be important for climate. It's where we get all our energy from. And there have also been changes in the way that the Earth's orbit itself is configured. Right now, we're closest to the sun during Northern Hemisphere winter and furthest from the sun during Northern Hemisphere summer. 10,000 years ago, that was reversed. So there are changes in the configuration of the Earth's orbit and tilt that could influence climate a little bit over the last 1,000 years. Probably not a lot compared to the last 20,000, the last 200,000 years. So the model simulations that I look at from the last 1,000 years to try to get at this question of how likely are megadroughts and how credibly can the model simulate megadrought are really focused on those terms, first and foremost, up until about 1850, and then human activities come into play as well, even as far back as the agricultural revolution. There's probably some influence of humans on the land surface, but especially in the intensification of agriculture we've seen over the last 150 years, changes in land from forest to cropland, or from pasture, and then this most recent period defined by increases in greenhouse gases in the atmosphere. So it's all there. It all gets put into the model. And beyond that, the model kind of just does its own thing. You prescribe these boundary conditions, the limiting conditions for the climate of the model, changes in land, changes in greenhouse gas concentration, little fluctuations in solar activity or volcanic explosions, orbital, and then you just let it rip and see what happens. Kind of like a video game that you're not playing, that you've written a program to play the video game for you. And this is what the time series of those fluctuations look like. So you can see the volcanic explosions are quite short-lived, but pretty powerful. For reference, down here, right there is the 1993 Pinatubo eruption. No Pinatubo fans / people that were born before 1993. That's okay. You get used to it. What I want you to see is that even the most severe tropical eruption over the last 30 or 40 years is nothing compared to some of these earlier, bigger eruptions. So we know that should probably play out in the climate model because it's changing the budget. It's changing the total amount of energy available to the climate system to move stuff around or to warm or to cool. There are fluctuations in the TSI's total solar insolation, which we measure in watts per meter squared. You can see the 11-year cycle as well as these longer-term 80-year and 200-year oscillations. The long-term trend, that's the orbital contribution, changes in the intensity of sunlight during the northern hemisphere summer and winter. So that's what's being shown there. And then rises in greenhouse gases, and then the very bottom here, changes in land use, which really, these last four only pick up during the, say, post-industrial revolution period. So it's all in there, right? It's all in there. And to give you a sense for what this looks like, I've got an animation which may or may not play, given the technical difficulties we've seen so far. It may or may not play. Let's assume that it will, on the off chance that I'm right. And I will explain what it's going to show, and then you'll actually see what it's going to show. And if it fails to play, then I'll explain what it would have shown. All right, so you can imagine at every year, you've got in this case 1,155 years of data. If you look at the data every year, it's going to be really patchy. It's going to be a lot of climate variability, a lot of change from one year to the next. What I've done is I've just smoothed out these maps through time to capture that low frequency component, the low notes of climate. So this animation plays, and it is playing. Great. Whew. What you're seeing is that smoothed out, that filtered low frequency variability. And there's some ups and downs, and your eye's probably drawn to the North Pacific Ocean or the tropical Pacific Ocean, where you get some warming that's followed by cooling. And up at the top, this is the budget. This is like the income of the model in terms of radiative energy, solar energy coming in. These little ups and downs, that's the total contribution of solar variability. So when people talk about like, oh, the sun's changed a lot in the past, like not the recent past. You got to go back billions of years to see a big change in solar output. And then there's these volcanic eruptions, some of which look kind of interesting, and 2 or 3 of which are coming up, look very interesting. So we'll stay tuned for those. Just a second. 1258. Wait for it. So and this is smooth data, right? So these are real big perturbations in the model to sea surface temperature. And we know for a fact, we know quite well that sea surface temperature is going to have an impact on other components of the climate system. All right, there's another one coming up. We can wait for it, just because it's fun. It's like a degree of cooling. This is one of the reasons why we know geoengineering will work, right? Big volcanic eruptions, good proxy for what we would do if we sprayed the atmosphere with a bunch of aerosols to just counteract the effects of climate, of greenhouse gases. It's a little bit like cutting off your head because you have a headache. So in my field, there's a big long-standing debate between, you gotta do the geoengineering disclaimer, because I'm like pro-geoengineering. I'm like, let's go to a tropical island and experiment with climate. It makes you sound like a supervillain. There's a big debate. There's a long-standing rivalry between the world of people like Connie Woodhouse. I don't mean to pick on her specifically, but she's in this picture. She's one of these, hardcore dendroclimatologists, mentor, co-author of mine. A lot of respect for her. She's there in the San Joaquin Mountains coring trees. People like her who are really embedded in the data, and the world of climate modelers who, I have tons of respect for them, very many colleagues and co-authors at places like NCAR. generating and running these simulations, and they often get into little wars with each other because their data don't often agree about what the important climate information is. So there's this long-standing rivalry, this long-standing debate about many, many aspects of the climate system that looks different whether you're taking a proxy view, paleoclimate view, from the data side or whether you're looking at it from the model side. And my workaround to try, I guess I'm averse to conflict or confrontation. So my way of trying to maybe bridge those two disciplines a little bit better is to come up with empirical or observationally driven null hypotheses for asking how much, what would we see in terms of megadrought if all we had was just the statistics of the last 50 or 60 years. How much megadrought variability would we see? How likely would these events be if the only show in town was the sort of range of variability that we've seen over the last 50 or 60 years? And so you can think about this like rolling the dice, except instead of having two numbers, you've got the whole climate system, right? Moisture, sea surface temperature, the whole lot of it. And that should give you a benchmark against which you can compare both the models and the paleoclimate data and see if they agree in some general sense with respect to a null hypothesis. These are multiple realizations of a phenomena, Nino 3.4, so this would be like El Nino phenomena, which has an impact on drought. And we use that to generate confidence limits. So our baseline expectation, drawn here, don't worry about the y-axis here, just think of it as like variance or variab, according to my slides. And these confidence limits are the range that you would get in terms of megadrought variability just from this null hypothesis of rolling the dice of climate many, many, many times. And when we look at the reconstructed PDSI, I might need to fix it. I'm not going to fix it. What do we have, like 15 minutes left? We have 10 minutes left. I'm not going to fix it. The reconstructed PDSI, which is a Palmer Drought Severity Index, this is a time series of drought through the last 1,000 years. It's within the confidence limits. So the range of drought variability is within the confidence limits. And that's kind of encouraging because it means, well, maybe if the proxies and the models agree in this space, then we can say something more robust. But it turns out there are limitations, actually, with that particular data product. And they relate to the way that biological growth is removed. And when we went through the stepwise procedure of getting rid of biological growth, they're removing a lot of it to be able to have a statistically homogenized data product to use to reconstruct drought. And in so doing, the low frequency end of the climate system is also being removed. And there's more low frequency variability, we think, from other types of records where that isn't a problem than is seen in that Palmer Drought Severity Index data set. But we can still compare this with the models. We can still say, okay, well, this is the range that we get from the proxy world, the world of people who go out and collect samples in the field and come back to the lab and analyze them and have spent their careers doing so. We can compare this range with that is simulated by the GCMs. Again, these look ugly. The take home here is that the GCM world is very much consistent with that null hypothesis. So even though you saw those really big eruptions probably playing out in important ways for the climate system, the total amount of variance, the total amount of variability that imposes is small compared to just the natural fluctuations themselves that you would get from the statistics of the late 20th century. The take home from this one is that the debate isn't settled. So this dashed line is like the world view from the proxies, and this mixture of lines of different colors from different models is the world view from the GCM community. And they fundamentally still don't agree, and the pieces don't fit together. So my null hypothesis has done nothing to try to bridge together these two. The Montaguillos and the Capulets are still at it, unfortunately. But we did learn some interesting things, and namely that to first order, the models are not necessarily giving you megadroughts at a much higher rate than this 1 to 2 times per century. And that's good when we look at climate change, because it means they're probably not overestimating the likelihood of megadroughts when we look at climate change scenarios. This is an animation of soil moisture. And I'm really close to finishing up here, so I'm going to play this animation. It's of soil moisture throughout the US during climate change, averaged together from a bunch of these different global climate models. And, whoops, I'm going to connect it to risk in just a second. But for now, just know that brown is dry, drier than today. This is the historical period, 90s, 2000s. So brown is drier than today. But when you run these models in climate change mode, with increases in greenhouse gases, they tend to simulate soils which are on average much, much drier than anything seen during the historical period. And that sounds a lot like megadrought, like permanent megadrought. Now, that's not the whole picture because these are relatively infrequent, unlikely events to begin with. So to estimate their statistics, we use a statistical method, Monte Carlo method, to combine the forced changes from the GCMs with emulator of the precipitation variability and look at the likelihood of megadroughts for different scenarios. Now I want to draw your eye down to this one, where in the Southwest, the probability of precipitation alone causing a megadrought, not even factoring in the role of higher temperatures, just factoring in the changes in precipitation alone, we get something like 30 to 50% likelihood, much higher than that 1 to 2 times per millennium. We published this paper, it got a lot of attention. It has a similar result for the global view. We're not alone in being exposed to those levels of risk in the Southwest. Much of South America, South Africa, Australia, parts of the Eurasian continent are in a similar ballgame to us. Turns out, when you publish a paper and you have quoted Wikipedia a year earlier, it's fair game for USA Today for their cover. As it turns out, this is a note of caution. If you read a quote from Wikipedia and it says a threat to civilization, then you, the person reading the quote, have said a threat to civilization. You've been warned. This attracted some critiques by my colleagues at Lamont who said, you're only looking at precipitation. That's not the full story. It's much worse because the role of temperature drives out moisture. And you haven't even factored that in yet. So let's redo the analysis and factor in temperature's direct effects on soil moisture using a bunch of different metrics, not just this Palmer Drought Severity Index, but soil moisture at different levels in each of the models, use all the models we can get our hands on, and compare it with the reconstructions. That's this Palmer Drought Severity Index, which is from the tree ring data for the last 1,000 years. Let's compare it and see what we get. And sure enough, they were right. It was much worse. The drying in the Southwest is unprecedented if we continue the course of climate change that we're on now. It's unprecedented in the last 1,000 years. Probably more like the last 6,000 years, but certainly in the last 1,000 years, there's nothing like the kinds of climates we would expect to see by the end of the century if we continue on our current course of using the atmosphere as a dumping ground for excess CO2. And of course, this weights the dice towards making megadrought much more likely. These are just probabilities of megadrought once you've changed the background state of the climate system to be drier. And the likelihood of a decadal drought, which in the past has occurred 1 to 2 times per century, over any given 50-year period is like almost 100% after the second half of the century. And the same for the multi-decadal megadrought. It's not as high, not quite as high, but it's still very, very high. And this reflects the fact that the mean state, the baseline against which you're comparing, has changed. So that's the bad news. The good news is that because the role of temperature is so substantial in drying out the soils in the Southwest and probably other parts of the world, efforts to mitigate and slow down and curb climate change actually have a positive influence on megadrought risk. And what we're showing here is 2 different scenarios. One where emissions just kind of keep chucking along where they're going. And the other one is one where we're much more aggressive about making cuts. These are the 2 end members. And it keeps the likelihood of megadrought, which is being shaded here, so yellow is like 100%, blue is 0%. It keeps those likelihoods much lower. It doesn't bring them back down to 0 or 10% or 5%, but it keeps them in a much more manageable realm than if we just let it rip and continue using the atmosphere as a dumping ground for wasted CO2. I want to finish up with some thoughts about megadrought and human nature, humankind. We evolved not far from this location. This is a goat in Ethiopia. Our species endured a lot of very interesting, from a scientific perspective, climate change and variability in East Africa. It's probably one of the many reasons why we have these big brains, big expensive brains. We have to be able to think through hard, challenging problems, climate changes that affected our ancestors' 10 to the 16th or something. It's probably linked to how we came to be. Megadrought itself is probably somewhere like in our DNA. And under climate change, the place we're going, if we just keep burning fossil fuels at the rate we're burning them now, puts the likelihood of megadrought into the levels that have never been experienced by any humans ever, for as long as there have been humans. It actually creates climates on planet Earth that are unlike any climates that have existed in the whole long history of our species. Tens, hundreds of thousands of years of our species. We're entering in a world that no human beings have ever really encountered before. But that being said, we're able to manage water in very different ways, and we're able to adapt and respond to the pressures of climate change, and we're probably able to mitigate it and stop it if we're really serious about it. And so I am not particularly pessimistic, despite all of this, that at some future paleoclimatologist talk 20 or 50,000 years from now, there'll be a Homo sapiens skull here. And I think we can manage the risks of climate change and megadrought. I think we can stabilize the climate system if we think about how we're producing energy being really critical to how we cope with the growing population, the demands for a healthy and nutritious diet, and not end up like the at least five other upright walking, tool using, language using sapiens or hominids that once occupied the similar niches to us in these volatile climates of East Africa. So I will leave you with that, and I'd love to answer questions if you have them. Thank you very much.
We have a microphone for questions today, so just raise your hand and I'll bring it to you. Anybody have any questions for Professor Toby Ault?
I'd like to tell. I don't like to tell people that Ithacans live in a what's likely to be a climate refuge. But some of the maps you had up there, the modeling showed even, like right up to just south of Syracuse being heavily drought affected under the worst scenarios by 2095. White Mountains might make it. Should I be buying land in the White Mountains? How much faith do you put in those things?
I always get a version of that question, whether it's talking about hurricanes or megadrought, or sea level rise, or heat waves, or disease, and I always dodge it. Think of it this way: the drought in California that's been unfolding for the last 4 or 5 years is not necessarily severely crippled certain sectors of agriculture in California. And the reason for that is that they have infrastructure in the Southwest that encompasses a very large geographic domain and is a significant fraction of the total amount of rainfall that they get, snowpack that they get. It's like 300%. In the Northeast, we don't have nearly as widespread infrastructure for moving water around, managing water. It doesn't mean that we're protected or we're not protected, but I think the kinds of droughts that have affected the West, if they were to occur even on short time scales, a few months, one season in the Northeast, would have much more devastating consequences. And you can imagine the competition for water between, say, growers and farmers and a nuclear power plant that needs that water to stay cool. Who's going to win, right? So we have those issues that we need to think about in the Northeast. That being said, there are certain things, you're right, that buffer the worst impacts of climate change. But there's also things that make us more vulnerable. So I don't know where the winners and losers end up in this game. I guess Siberia is probably, No, we all win. If we stabilize the climate system, if we manage it responsibly, we all win. We feed a population of 10 billion a healthy and nutritious, ample diet. And we do it with green sources of energy that don't use the atmosphere as a dumping ground for waste CO2. That's what we do. We all win. Yes?
Well, I'm assuming that somebody is keeping track of aquifers, right?
Unfortunately, the aquifer situation is very bleak.
Well, because you're talking about distribution
Yep.
of water resources,
Yep.
and of course one of the main major resources in California and
Yep.
elsewhere is aquifers.
Yeah, the aquifer situation is very depressing. It's just very depressing. They're not recharging at the rate we would love to see them recharging in some of the most vulnerable places. So yeah, people are, and you can see it with remote sensing. You can see it with satellite data with gravity inferred water levels. The pull of the water on the spacecraft itself, on the satellite itself, has decreased because the water's gone, and so you can infer how much water has been removed. And we don't really know in a lot of those places how much is left. And those are a lot of the dry places that are central to agriculture and have very densely populated cities and regions nearby. It's very troubling to see the aquifer situation unfolding. And that doesn't even factor in places that are like island nations that are even more limited in their access to water. Yes?
So you just referred to proper management. We
Yes.
will all win with proper management. And
Yes.
Yet you've got factions of researchers that can't even agree. What's your proper management?
I think disagreement is important to proper management, personally. I mean, this is my own view, right? I think disagreement's good.
Brass tacks. How should it play out with people's lifestyle changes? And
Well, so are you asking me to weigh in on how people should use water in the
that's
Southwest?
one.
I will tell you a story that my mother-in-law, stay tuned, told me. So my mother-in-law lived in Greenwich Village in the 60s. Sounds cool. And she remembers the drought from the 1960s that was pretty painful for New York City, and the signs in the subway that said, "Save water, shower with a friend." We have a good relationship. The reason I think that that's an important story is because it does say there's a lot that can be done on an individual basis in the area of water conservation. And if you compare cities like Tucson, which is has water management, water conservation embedded in the culture. People are using gray water for their orange trees. To a city like, I don't want to pick on any one city too much, but let's just say Phoenix. The culture around water is very different, and it's changing. And there's a lot that can be done and a lot to be said for individual choices putting more value on fresh water, as they should, because it's this amazing stuff that falls from the sky for free and that we can drink, stay hydrated, grow crops, make power. But it does have an individual level component to it, as well as this macro, level management, which can get complicated in the politics and drag down the politics. But I think the disagreement too, I said the disagreement is good because I think that an important component of good management is good science, and good science has disagreements.
Toby, we have a question here from the WebEx. So when you look at climate, sort of similar to what you just answered, when you look at climate models that suggest widespread drought in North America over the next 100 years, what do we do with that kind of information? Is an outcome like that preventable?
Yes, don't use the atmosphere as a dumping ground for waste CO2. That's the short answer, right? If this is a consequence, very direct consequence of rising temperatures, which move storm systems around and make it drier because there's less precipitation. But even more importantly, more centrally than that, there's this, in the Southwest anyway, direct effect of a warmer atmosphere driving out more moisture from the top layer. Someone over there.
I have a question. I just want to follow up on what you just said about individual choices about water conservation. It seems to me that most fossil fuels are burned by really large industrial corporations, and most water use, not most, but a significant amount of water use is in manufacturing and other forms of industry. And while individual choices are part of the solution, it seems like just people changing the way they live isn't going to solve the whole problem. So can you talk a little bit about that issue in terms of water conservation specifically?
In terms of water conservation specifically? It's a great question. I think where individual choices matter the most is in sort of two arenas. The one that I just mentioned, okay, you're right. There are much larger scale water users. You're right. When we make choices about how we use water, or how we, what kind of food we eat, or where our food comes from, how we get to work, we send a message. We vote with either our dollars or our time. We vote with our dollars or our time every day, dozens of times each day. And companies, the mega corporations that they are, pay attention to how we vote with our dollars and our time. And so there are individual choices, not just in the area of water specifically, but I think relevant to water. If you, for instance, know that product A, I'm not going to use specifics, product A consumes a huge amount of water and is very intensive in terms of its demands, and it's from a region where water is an issue, versus product B, which maybe doesn't quite have the sparkly flavor that product A has, but is generally better for the region, for the planet, and you choose product B and you keep choosing product B. I mean, yeah, we live in an economy where people who make decisions about what to sell and where to sell it are gonna start paying attention, and the organic movement is a great example of that. Where, you know, when I was a kid, it was the access to organic food and gluten-free, right? The demand for these kinds of alternative food products has risen so much that they are just widely available. You can get gluten-free pasta at you know, the gas station now. That was not the case not so long. Well, I don't know. You decide. I think it wasn't so long ago. So I think that's where individual choice comes into play, both what we consume and then what we do on a daily basis, because it has a sort of a tangible impact on our capacity to cope with extremes. In LA, not watering lawns, which was mandated, but they didn't do it, the municipal water use stayed sort of much lower than it would have, or is projected to, when they were screaming about running out of water by the end of last summer. It didn't happen. That's partly because of individual choices. But that's in crisis mode. You know, it's a little bit different. I don't know, does that sort of help? Okay. So I think someone in teal had a question. Is that the right color? Is it teal? I'm not good with colors.
That's really loud. If you're defining a mega drought or a drought in general based off of its deviation from the average,
Yes.
how many years into the future do we continue to get drier and drier and drier climates before
It stabilizes?
instead of calling it a drought, it's just part of the new average?
Yeah, I think that's a very subjective question. I mean, that's going to have a subjective answer. Again, it depends on the water management application that's been envisioned. So let's say I'm 35-ish. And my definition is 35 years, right, for megadrought. So if there had been a drought for my whole life in the region that I was living in, and I only knew this because of my parents or my grandparents told me it used to be wetter and now it's not, I would probably just think that was climate change. Now, it turns out it might not be. It might actually go back to some wetter reality. Where I think the timescale becomes more important is now, because when we're thinking about planning for and adapting to climate change this century, climate change is already unfolding. We project 35 years out. Well, another 35 years, that's the middle of the century. It's 2051. It's not that far away. And so if the risk of something like a prolonged drought is high, you might make a different set of choices right now, whether or not things unfold, than you would if the chance of such an event were low. Now, as far as adapting to changes in the baseline, I agree. I mean, there's going to be a natural progression towards coping with less and less water gradually through time. And we'll probably see it in the extreme years. We'll probably see it in the extreme events like the last few years in California, where real significant changes have occurred. And to credit the Californians and Californian water resource management, really the world has been looking to California for solutions to cope with water shortages. Decreases in snowpack, not enough moisture, and you can say what you will, but there's I think a mismatch between what was projected to happen 18 months ago and what's actually happened because of under extreme duress, extreme stress, management strategies came into play that prevented the worst, most catastrophic impacts from occurring. But that's being very reactive. That's reacting to a stressor, not getting out ahead and planning for it, in a proactive way.
Okay, so I guess sort of bouncing back to that gentleman's question over there, I guess there's a lot of students here who work on finding food for the dining halls that have low carbon footprints, low water footprints, but it's actually extremely difficult to figure that out for our food sources.
Yep.
So how are individuals supposed to make the right choices and impact the change that we need to sort of save the species?
In terms of how do you know what the carbon or water footprint is of a particular product?
Well, I guess just more generally, if individuals don't have the ability to make decisions food-wise, just in their own personal lifestyle,
Right.
is there another alternative answer? I mean, the stakes are pretty high.
Right. I think that I'm gonna not quite answer your question because I don't think it has a great answer, but I think that there's another question that I'm going to answer that maybe helps you with that one, which is information is key. Okay, good information, reliable information is key, because if you know product A has a water and carbon footprint of X, and product B has a water or carbon footprint of Y, and Y is much less than X, then you and everybody who you work with to make responsible, sustainable decisions for the university is going to naturally gravitate towards product Y because of its lower carbon footprint. But that's something like that requires labeling, right? That's like a simple example. It's a simple application of labeling. How do you know that food's organic? I mean, if you were trying to find organic food before the organic label, you'd be in the same situation that you're in now. How do I know it's are you going to source every single product that comes into the university by going down to the farm level and tracing back whether or not their practices qualify as organic? No, we have a shorthand for that. It's the organic label. Same with the Rainforest Alliance label that goes on the chocolates and the farmer whatever co-op for coffee. Right, so these are labels that I think have really significant impact already in consumer decisions to date. And if there were the equivalent types of labels or just information right on the products themselves for carbon and water, we would see people like yourself and the people you work with making different choices, and that would feed back into the larger scale system. I think. I mean, that's missing right now, but I think it's an important piece of the puzzle, which is information, good information, reliable information.
We have a WebEx question.
Yes.
So we have a WebEx question. Is it on? Okay. Thinking about natural resource management in an era of climate change, I observed that lately in the discussion around climate change, the topic of overpopulation has been somehow let aside. And it certainly impacts water and drought in the Southwest, issue of overpopulation. So what do you think about that?
Do I want to tread into the gray area of population? How to answer that one with that? That's a hard question. I mean, what are you gonna say realistically about population that isn't somehow offensive, right? Yes, population growth is going to put major demands on energy and food and water resources in the future. No question about that. Let's just be honest. It's going to be 10 billion people by 2050. The question is not whether or not we should think about population control, because I think that's draconian and somehow can be just completely misconstrued. I think what we should be thinking about is how are we going to meet the goals of feeding 10 billion people a healthy, ample diet and giving them access to energy on the scale of the, say, average Cornellian student, right? It's a question of, or less, half of that. I mean, whatever level we agree on as an international community is an appropriate level of access to energy, because energy can do wonderful things like power hospitals, among others. I think let's start from that point of the discussion. And I'm sorry, WebEx person. See, it's like if they're here, I probably wouldn't be so animated in my response. I'd be much more measured. I apologize to you, lucky person of the internet. I'm not. I think it's a great question. I think it's obviously a great question, but I think it needs to be addressed in this context of realistically, there are going to be a lot of hungry mouths this century, and there's going to be a lot of. There's either going to be a lot of suffering, or there's going to be a lot of really great solutions that come into play to alleviate that suffering, and that's the conversation that I would want to have.
As a society, it's pretty clear that we wait until the danger is right in front of our face before we do anything.
Right.
We're starting to see, say, with Hurricane Sandy, and maybe more recently with sea level rise, where that's enough in front of our face,
right.
That it's a motivating force to action. Drought with California is maybe starting to rise in the American consciousness.
Sure.
What would be your guess? How many years will it be before the level of drought that we're seeing is a motivating social force to do something about carbon?
Well, about carbon specifically?
Well, carbon dioxide, global warming.
About climate change, where drought becomes the incentive to reduce. To put an estimate on the amount of time it might take is not, it's sort of beyond my area of expertise. But I will say, though, there's two things, though, that I will say. One is that the drought that has happened in California now is in a lot of ways a taste of what might come if we just stay the course. And because it's just a taste of what might come, first of all, hopefully it motivates management and policy and voter communities to not go that path. But second of all, because in the case of megadrought, we know these things have occurred in the past. We're under extreme stress right now with the current drought. It's a taste of what's likely to come. And in that sense, whatever policies and practices and management strategies come into play now because of the current drought will be highly relevant for coping with and adapting to climate change in the future. Just in the same way that, you go to the gym and you do a bunch of, exercises, and then the next time you're a little bit stronger because you got this workout, you strengthen the muscles. I think what's happening now in California is strengthening some of the management and infrastructure around the area of water, and that will be valuable if we continue, whether or not we continue the current course, because it helps build some adaptive capacity or resilience into the system itself. So in that way, there's I don't know what the right word is. I don't want to say advantages. There's lessons that are important from the current event. But as far as in motivating change, it goes outside my area of expertise. Well, what will actually motivate change? I think when we get to that point, it could go very quickly. And I don't know if we're there now, or we will be in another 2 years, or if it'll be 5 or 15. But once that change starts to unfold, I think it could be a very quick turnaround in people demanding solutions.
But you use numbers, you're not saying 50 years, you're saying 15 years.
I'm an optimist, so I'm not going to say 50 years, because if we wait 50 years, we're entering it's a different conversation. If it's in the next 10 or 15 years, the conversation is still around how do we stabilize climate by producing energy in a way that doesn't use the atmosphere as a dumping ground for waste. If we wait 50 years, the conversation is, I don't know what the conversation is. It's different.
I think we might have time for one more.
In climate modeling, with variability inside or outside of that drought process?
How do we do? So that's a great question. Come work on it in my lab. It's a good question. It's a scientific question there. That's basically, how do you try to think about extreme precip during a drought? Because we're looking at the long-term average, and it's certainly possible that in the future we'll get mega droughts and extreme rainfall. And that kind of goes outside the scope of the way that we conducted this particular analysis, but it could be critical for water resource management to know that, it's going to be dry on average, but every now and again you're going to get these huge rainfalls, and therefore we need a different type of system for harvesting and holding on to that water. But it's an open question.
And you're working on it?
Yes.
So what do you think?
I think it's exactly that. I think that I don't know what the infrastructure looks like, but I think that the statistics support the idea that we would get more extreme rainfall events even with a drier background for a lot of the Southwest. So that you move the baseline down, but then you get these big peaks.
So how do you store that water?
Are there engineers? I assume that they assume that it has to be a combination of engineering and water resource management in a general sense that lets you cope with that. Because right now in the Colorado, something like 300% of use is stored. I don't remember the exact numbers, but it's a lot. It's a very significant fraction of what's used gets stored in the big reservoirs there. And a lot of them are open, right? They're just open. And there's a lot of loss from that. And it's also adapted. It's really tuned to the idea, to the historical fact that most of that precipitation arrives, or a lot of precipitation arrives as snowpack. If it's going to be coming flashier as rainfall in the future, then it's different infrastructure to cope with it.
What about trees?
Are they good or bad? I like trees.
Storing water.
Can we store water in trees? Oh, you mean as far as soil health goes? Yeah, I think soil health is probably a big part of the story. I agree. Yeah, soil health is probably an important part.
All right, well, let's thank Toby one more time.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.